continuing with our Fundamentals of Engineering Statics coverage of some complex vector problems. So if you want a refresher on this, go take a look at our previous week's videos. We cover vectors in a little bit more detail. But what we're going to do now is we're going to use some vector tricks that we've solved in previous weeks and apply them to this more complicated statics problem. So a lot of times my students will look at this and they'll immediately think that this is a super complicated problem, really difficult to solve. But actually, if you make some simplifying assumptions as you move through it, you'll see it's a quicker problem to solve than it appears to be. So we have this crate, this box, that's suspended from the walls by 3 cables. And we can see that these 3 cables are meeting at what I've put our axes on. We'll call this our origin point D. And we are looking for the x components of cables BD, so this one here, and CD, so this one here. So we're looking for the total of the x components of the tension in those cables. And we know that the tension in AD, the full tension in that cable, is 9,000 newtons. So how are we going to solve this? Well, if we look at the axes that I've drawn in here, we can say that this is x, this is y, this is z. And if we extend our z-axis, it's kind of hard to see in this image, but if we look at the components, we see that our 3x components paint a clear picture. BD and CD are on the positive right-hand side of the x-axis. They have positive x values. And AD has a negative x value. So this problem is asking for the sum of the components of BD and CD in x. So their sum is going to be the same as AD in x. So all they're really asking us to find is AD in x. And AD total is already given there. So that makes it a much simpler problem. So our process for working through this is going to be to find our vector. We'll call it r. We're going to find our r vector, and that's going to be based on the length of this cable. And then we're going to find the magnitude of r, which is directly the length of the cable. And we're going to use that to define a unit vector. And then we'll use that unit vector to find our force, which is what we're looking for. So one step at a time, let's solve for the vector itself. So to get the vector, we need 2 points in space. We have our origin here at 0, 0, 0. And then we have our point A, and we'll call this x2, y2, z2. And then this is obviously x1, y1, z1. So we have our 2 points in space. And our resultant vector is going to be x2 minus x1 plus y2 minus y1 plus z2 minus z1. And we can see that because 0, 0, 0 is our x1, y1, z1, this becomes a little bit more trivial. So our vector is really just negative 15I plus 8j minus 4k. So now we have our vector. And if we want the magnitude of that vector, remember we're going to do the square root of the sum of the squares. And that will equal out to about 17.46 meters. So now we have our vector, we have its magnitude, and we can solve for a unit vector that gives the direction. It's just the vector divided by its own magnitude. So we're going to have negative 15I plus 8j minus 4k all over 17.46. And we're going to do this division one component at a time. So negative 15 divided by 17.46 gives us negative 86I. 8 divided by 17.46 gives us positive 0.96j. And negative 4 divided by 17.46 gives us negative 0.23k. So now we have a unit vector. I'll rewrite it over here just so we have it because we're going to need it now. And that unit vector will define the direction of this cable length from A to D. Now, the magnitude of that unit vector is 1. That's what makes it a unit vector. But it gives us also the direction of our actual force vector, which is along the same path as our cable length. And the interesting thing we can do now is if we want the force vector, we know that our unit vector is our length vector divided by its magnitude. So we can say that our force vector is the unit vector times our magnitude. And in this case, the magnitude is really the magnitude of the force, which we know from the problem, it was written in the problem statement, is 9,000 newtons, right? That's what they said that the force magnitude was in AD. So if we want to solve for the full force vector, we would multiply u, which we have right up here, by 9,000. And we're going to do it again, just like we did before, one term at a time. So negative 0.86 times 9,000 is going to give us negative 7740. 0.96 times 9,000, positive 8640. And negative 0.23 times 9,000, negative 2070K. So now we have our vector of our force, which combines both the magnitude, the 9,000 newtons, and the direction. So if we took the sum of the squares, square rooted it, we would get 9,000 because that's our magnitude. If we divided this by 9,000, we'd get back our unit vector that we had for length. So now it's quite trivial. They're asking us for the combined x direction. That's just this value here. So AD is negative 7740 newtons to the left, and BDX plus CDX, which is what they're asking for, is the same amount, but to the right, positive 7,740 newtons. So just a nice relationship that we can get between the length and the force that's being transmitted along that cable length using our vector definition, its magnitude, and its direction. Enjoying these videos? Follow the links in the description below to find out how you could reach out for personal tutoring, like and subscribe to get notified when new videos drop, and comment with suggestions for future topics.